Okay, welcome back to our Chapter 3 Physics video, where we are looking at two-dimensional vectors, and we're going to pick up here on scaling vectors, or multiplying by a scalar. So here we have a vector v. I can call this v1. I can add one subscript here. It's going up and to the right, and it is whatever its length is. Its magnitude we'll just say is 1. Okay, so if we multiply v1 by 1.5, 1.5, what does that do to it? Well, it doesn't change its direction. It still has the same direction, still has the same angle, it's still going in the same up and right direction. It's just that its magnitude increased. Now instead of being 1 unit long, it is 1.5 units long. And if we were to multiply v1 by -2, it's now 2 units long. It's now twice as long as it was to start with. But its sense has changed. The direction, the angle is still the same. The angle, for instance, theta here, that it makes with the x-axis. But the arrowhead is at the opposite end. So multiplying a vector by a negative scalar changes its direction. Multiplying it by any scalar changes its magnitude, unless that scalar is 1, I suppose. Okay, so we have looked at taking horizontal and vertical vectors and combining them to get a resultant. We add the two of them together and we get this diagonal resultant. As it turns out, when we are going to need to add vectors together that are given to us as diagonal, what we are going to need to do to these diagonal vectors is break them down into vertical and horizontal components. So in other words, we're going to have to sort of do the reverse process of adding vectors together. We're going to have to take this diagonal vector and find out what is its horizontal and vertical components. So this vector right now is going up and to the right. We basically want to know how far up does it go and how far to the right does it go. And we can do that using trigonometry. So here we have the diagonal vector, its vertical component, and its horizontal component. And those three vectors together make a right triangle. Here is our right angle. So the side across from it is the hypotenuse. And we're going to describe the direction of the resultant using this angle theta. So if you remember from trigonometry class, TOA, that's a way to remember that the sine of an angle is opposite over hypotenuse. So if we look at the angle theta, the opposite side is Vy, the y component, and the hypotenuse here is the magnitude of the resultant or original vector v. So sine of theta is Vy over v. Cosine of theta, CAH, cosine is adjacent over hypotenuse, so that's Vx over v. And tangent, TOA, TOA, is opposite over adjacent, so that's Vy over Vx. Then we also have the Pythagorean theorem here. The hypotenuse v squared is equal to the x component squared plus the y component squared. So if we are wanting to know what the x and y components are, we can find them using these two equations. So theta, to get theta by itself, we would just need to take the inverse sign of the other side of the equation. Theta is no, we're not trying to find theta, sorry. Scratch that. We want to know Vy. So Vy is equal to, just multiply both sides by v times sine of theta. And if we want to find Vx is equal to v times cosine of theta. So I always recommend using theta x. And what I mean by that is that when you have a diagonal vector and you're trying to find its x and y components, you should always refer to the angle that the vector makes with the horizontal, not the angle it makes with the vertical. So this over here we would call theta y, the angle with respect to the y-axis. I tend not to use this one. So don't use this one. The reason why is because if you always use theta with respect to the x-axis, then the y component is always found by multiplying the magnitude of the vector by sine of theta, and the horizontal component is always found by multiplying by cosine of theta. And so if you always use theta sub x, then x will always be associated with cosine, and y will always be associated with sine. If you use the angle with respect to y to describe the angle of the vector, then sine and cosine get flipped. And I just think that it's very easy to confuse those two and use the wrong one. So if you always do the same thing, it helps you to remember. So that's what I recommend. Whenever possible, use theta x, and that way y is sine and x is cosine. So the reason why we need to break down vectors into their components is because if we wanted to add v1 and v2 together, so here we've got our vector 1, it's diagonal, it's up and to the right, and we want to add it to v2, which is also diagonal, up and to the right. It's going to give us this resultant, starting down here and ending up here. The direct line from beginning to end is the result, BR. But how do we quantify this? How do we know what its magnitude is or what its direction is? Well, if we take V1 and we break it down into its x and y components, and then we do the same for V2, we break it down into its x and y components. If we add this x component and this x component over here, the two of them together added up, this horizontal length and this horizontal length, add together to give us the horizontal component of the resultant. And the same thing in the y direction. If we take the y component of our first vector and the y component of the second vector, and we add the two of them together, this vertical length and this vertical length added together give us the vertical length of the resultant. So by breaking the two vectors down into their x and y components, and then summing the x components and summing the y components, we get the x and y components of the resultant. And then from there, it becomes just a resultant problem, finding the resultant of these two perpendicular vectors. It creates a right triangle with the resultant being the hypotenuse. So we can find the magnitude by the Pythagorean theorem, VRY squared plus VRX squared. Take the square root of that, and it gives us the magnitude of the resultant. And then to find the direction, theta, of the resultant, we can use the definition of tangent, opposite over adjacent. So theta sub x is going to be equal to the inverse tangent of the opposite side, VRY, over the adjacent side, VRX. This is just a little visual image I like to think of to help me keep this straight and remember how to find the x and y components. Again, I think the reason why I like to visualize a cannon is because a cannon sits on level ground, and we measure how far up we're aiming the cannon by this theta x that we're measuring with respect to the ground, not theta y. We're not measuring that angle. That's not the one we want to use. We want to use theta sub x. And when we do that, the horizontal component can always be found by taking v, the magnitude of the vector, multiplying it by cosine of theta. And the vertical component can always be found by taking that magnitude and multiplying it by sine of theta. So again, it's very easy to confuse these two and mix them up. I like to always stick with theta sub x, and so horizontal is always cosine and vertical is always sine. So here is a 6-step process laid out by the textbook for adding vectors. This is adding vectors by the method of components. You want to draw a diagram and add the vectors graphically. I think that's really important. So if you've got one vector going this way and another vector going this way, the resultant is from the beginning to the end. Okay, so we've got like vector 1, vector 2, and the resultant. Choose the x and y axes. Okay, so a lot of times that will essentially be given to you in the problem statement, or maybe the problem describes things as like north, east, south, cardinal directions like that. So set up your x and y axes, and then resolve each vector into x and y components. I recommend using a table. So set up vector 1 and vector 2 as the rows, and then the columns can be x and y. And then you can write in the x and y components of vector 1 and the x and y components of vector 2. And then you can add up or sum those two columns to get the x and y components of the resultant. So resolve them into x and y components, calculate each component using sines and cosines, add the components in each direction. That's where we get these two sums. And then step 6, find the length and direction of the vector. And we can do that by using Pythagorean theorem to find the magnitude. V equals the square root of vx squared plus vy squared. And we can find the direction using tangent of theta. If we just take this one step further, it is tangent is equal to, theta is equal to inverse tangent of vy over vx. Okay, and again, if we're finding theta sub x, the y is always on top, the x is always on bottom. If you think about the right triangle here that we're finding, theta sub x, this is the opposite side, y, this is the adjacent side, x. Okay, so I'm going to stop this video a little early because I don't want to be cut off in the middle of this example problem. This is a good stopping point here, and we will begin example problem 3.2 with the next video.